Hello, community. I received a question, how can I train my sentence transformer model, my SBERT model, on two different domains? Let's say you want to have your model trained on the domain 1 first. So your training dataset out of domain 1 is content specific, let's say mathematics or physics. And then you want to go on and train the same SBERT model on the content of another domain, domain 2. So we have a training data set of domain 2. How to do this? This is the content of this video. Now, at first, easy. We have, if you want to follow along, this is an official Jupyter Lab. So this is the link. Just click the link, follow along. I will leave you the link in the description of these videos. Now, first step is our dependencies. We have to install our sentence transformers. We have PyTorch, the version, and we have some data loader, some czip. So let's do this. And the first part here that we download a sentence transformer model that has been trained on the domain 1 is one line of code. We say sentence transformer to download from Hugging Face, and we choose the transformer model, the still BERT base version 2, and we want to have this transformer model fine-tuned on the NLI dataset. This is, of course, the Stanford Natural Language Inference Model dataset that also in the NLI version also include the multi-NLI version. But whatever. So the first part, domain 1, SBERT, we downloaded a pre-trained and fine-tuned on SNLI dataset from Hugging Face. First part done. Now, what we have, you can always check if you just specify the model. Yes, we have to download it at first. So you see download process starts. The model should come up sometimes here, 330 megabytes. The model is coming up, completely pre-trained and fine-tuned on the SNLI dataset. For dependencies, done. So if you now look at the model that you have a sentence transformer model. Easy, yes, that's exactly what we want. The transformer itself is a Roberta model. Yes, it is a distilled Roberta base version 2 model, a submodel from this. Now, here you see an interesting piece of information. The maximum sequence length as an input to the transformer is 75 tokens. So after 75 tokens, the rest of the sentences is cut off, ignored. This is a little bit on the short side. I would go a minimum with 128 or even 256. If you want to alter it to this, please see my last video. I think I was doing a 128 maximum sequence length. And the second module, of course, or the layer if you want, is the pooling layer. The pooling layer generates a fixed length vector representation. We have here a 768-dimensional vector representation, and our pooling methodology is mean. Great. So we have our first line, SBERT, fine-tuned on domain 1. So now comes the interesting part. Oh yeah, if you want to use this model, you can use it immediately. Let's say we have 3 sentences. Then you use this model. We download it. We said encode my 3 sentences. You get the sentence embedding in a 768-dimensional vector space. And if you say, show me the sentence and show me the mathematical embedding, well, here we go. Start at the very beginning. Oops. Here. Sentence 1. This framework generates n-dimensional embeddings for each input sentence. And then we have a 768-dimensional, here we are, 768-dimensional vector representation. And then we go to sentence B, the next sentence, and the next vector representation. So you see the model that we downloaded, the SBERT model, fine-tuned, perfect, ready to rock and roll. Now let's have a look here. Let's say that the third sentence, a brown fox jumps over a lazy dog, we have two animals. Let's say in the training sample of the first domain, there was nothing, no information about animals. So fox and dog and whatever is not part of the pre-training and fine-tuned. So you have to go and say, okay, I want to have an additional knowledge integrated. So now, if you want to train your SBERT model, let's say on the world of animals, that is a domain 2 specific content, you have now to train your SBERT model on anything that is connected, for example, with dogs. So you will be able to exactly find the perfect vector representation also of sentence 3. And this is what we're going to do now. So at first, easy. We have to get the training dataset. Now the training dataset for us will be a standard public dataset, SDS benchmark dataset. Here, this is the link. We download it. We say, okay, we later want to save it in a directory. Then we say we read the benchmark training dataset. So we have our CSV dict reader. And we say everything here, our training samples, just is an input example. And we append everything to this one. So the content is we have a sentence 1, we have a sentence 2, and we have a numerical value, a float that gives us the semantic correlation between sentence 1 and sentence 2, and I think it is between 0 and 5. So we have, of course, to normalize the score for the closed interval 0 to 1. Now, if you are not sure about this, always do some exploratory data analysis. Let's have a look at what is in these contents. Let's have a look how many unique sentences we have in there. So this is what we're going to do in a second. And if we say, okay, our training dataset fits our needs, then we say, okay, put it in a data loader. Here we go with our training samples, shuffle it around, define the training batch size, and we just have to define for our model the loss function. Now here we are lazy. We go for the cosine similarity loss function, the easiest one for our model. And this is it. Now, if you want, during the training, you want to have another evaluation dataset for the training period, you can go with now the development dataset within the SDS benchmark dataset, since we already downloaded it. And we say we have here a performance evaluator. We do the embedding similarity, evaluate it for our development samples. And our development samples we defined here. And you're not going to believe it, the final model we're going to train on the test samples of SDS benchmark. But let's go step by step. So we have our evaluator, we define our warm-up steps, and finally now we do train the model. So here we go. We say we have our training objective is we have a training data loader. We have defined our loss function. We have defined our evaluator, training data loader, training loss function, evaluator. We define the number of epochs for demonstration purpose, it's 1. We define the evaluation steps, I say every 20%, warm-up steps, and we save the model. And this is it. So let's do this. Now the first you see here, I have a look at my dataset. Oops. And I have a sentence 1. A sentence 2, and I have a score between those two sentences. Sorry that it's not in one line, but whatever. And as you can see, you have sentence 1, a plane is taking off, and the reference sentence 2 is an airplane is taking off, and the familiarity score, the maximum, is given with the indicator 5. And then for each sentence 1 and sentence 2 pair, you have here a numerical similarity measurement. If you then do okay, how many sentences do I have? You have here for sentence 1, the count gives you 8,628 sentences, and of course the same amount of sentences 2. Now out of these 8,628, only 7,977 are unique, and only 8019 and sentence 2 are unique. It is important you always check on the dataset. And then more or less the training is going on. And as you can see, it is going to take 35 minutes till this is done. And we do not want to wait, as something will come up. What I do now, I will change here my number of epochs. Where is it? To 4. I will stop this since I'm operating on a CPU only. I didn't want to waste some GPU power. And now let's say disconnect and delete runtime. Runtime, change runtime. Now we go for a GPU, for a free GPU. And then we say run all. And here we are. After 4 minutes, all my 4 epochs have been done. We've trained this model now for 4 minutes. Beautiful. What I want to show you is at first this model, we have saved this model when we tuned it in the output path. And this is some directory you specify here in Colab. I show you, I put it in the output directory and then have here continue training LNI. Distilled Roberta base version 2 model. And then you see here all my model with all the different files. We have everything from a vocabulary file in JSON, the tokenizer file in JSON. Here you have the model itself, 313 megabytes. You have the configuration JSON here. Just showed you, you have a Roberta model. You have a vocabulary size of 15,000. You have a number of attention head is 12. The number of hidden layers on your model is 6. And all the different specification. If you're interested in tokenizer, you can have a look at the tokenizer. Gives you an information of it's weekend, problem, download, my internet connection. Whatever you're looking for in your tokenizers, your config in general, vocabulary if you're interested. We have 50K vocabulary items, and you can see what it indicated as a specific token. So if you now, thank you. If you now store this somewhere in the cloud, this directory with all these files, you store continue training directory in your cloud. You do not forget the path to this. And then you say, if you want to reuse this model, you say sentence transformer. Now the path to this particular model that we just trained. And now we test it or we benchmark it against the test samples that we created just a minute ago. And we evaluate it against the test sample. So what we do is now we load a complete new sentence transformer model. It's now called model reloaded. And we run an evaluator on this reloaded model. And as you can see, you can save it also to a path or the same path. And we get a similarity or an evaluator from 86%. So quite nice on 4 epochs just trained. So very easy. Okay, now I do have, just hold a sec. So here's my picture again. So we have taken an SBERT model on a specific domain 1. This was our SNLI training dataset. And then we trained it on the same model. We provided the content of another domain. This was now the training dataset from the STS benchmark training dataset. And we have now a model that has been trained on both domains, on both knowledge content cluster, if you want. And this is exactly what we set out to do. I say thank you for watching, thank you for listening, and I see you in the next video.